board for Allison. She'll be able to catch up. Solve the differential equation. After you integrate, you have two things left to do. You have to plug in the point they give you to find C, and you have to solve for Y. It doesn't really matter in what order you do it in, because you should get the same value. Y of 0 equals 2. Is that true? Did I not write it like that? Do they say Y equals 2 when X equals 0? Oh, they say that. Perfect. Let's not solve for C yet. All right, let's do this. Ooh. Okay. You can solve for C now if you want, but I just want to show you that you don't have to. What would I do if I wanted to solve for Y on this? Just E it. And this is that whole exponential growth thing, right? Like this is e to the x plus c, which is the same as saying e to the x times e to the c. But e to the c is really just c, so that's why we can say this is y plus 2 equals c e to the x. So that's where that exponential growth model comes from. Solving for y, I would get y equals c e to the x minus 2. And then you can plug in your point. We could have plugged it up here. I can go back and do that if you did, and you want to see it. But it should work either way. I tend to solve for c early, but I just wanted to show you that you didn't have to. So now if I plugged in 2 here when x is 0, e to the 0 is just 1. So do you get that c equals 4? Which is what you get if you plug it up here, because you would get ln of 4, right, equals c, and then over there if you do e to the ln of 4, no, any clue what I'm saying? I don't know. You should still get 4. Which means your answer is the differential equation y equals 4 e to the x, right? That's it? Minus 2. Sorry, I couldn't follow my own work. Shouldn't work down and then go back up. Really hard to follow. Especially if you're grading that. Definitely you're going to see solving a differential equation on your test. With or without a calculator, because you could do either one, right? Multiple choice or free response. It's a really good free response question, like I told you. 9-point free response question, solving a differential equation like this, 5 or 6 of those 9 points. 17. X ln of x. I think the dx on top, but right, I moved to the side.
I just can't think of how to get started. Like, I don't know how to think we need a U substitution.
We need a u. So pick something for u. Maybe you want to pick the whole denominator, right? So you say, well, what if I pick this as my denominator? What would I have to do to take the derivative of that? Right, like this would never be a good u, because this means I'd have to do the product rule to take the derivative of that, right? That's never going to match what's over there, right? So you don't ever want your u to be complicated. You want your u to be a quick derivative. So if you tried that, you should say, okay, well, that's not going to work. So it's either going to be the x or the ln of x, and I hope you're starting to think about the derivatives, right? If I pick x, well, that's never going to match the ln of x. But Emily is right. If we pick ln of x, then look what happens when I take the derivative of ln of x. I get 1 over x. And that is in the problem. You have to think about that you can separate, right? That's just multiplication. This is the same as saying 1 over x times 1 over ln of x dx, right? Those are just all put together, but multiplication you're allowed to break up. So it's like a lot of it, I feel like, is visual, being able to see that that's there, which means this is a perfect u substitution, because all of this becomes my du, So that just becomes 1 over u du. Mason.
What's the dx? Like, what's that saying in the problem?
It's just the constant of integration that we put in there when we did Riemann sums, right? We talked about that was the change in x, and so that was like the width of your rectangle. Now that we're doing the exact integral, that's really more about a limit, right? Like the width of the rectangle is going to 0 because we want the rectangle to become the actual area. So when we integrate it, it really doesn't mean anything. It's just matching it up. It's just a constant of integration. Well, if you're writing an integral, you have to include your constant of integration to get your points on it. And so it's just some of the notation that we use. I don't really have a better example of that except for when we changed from Riemann sums, right? Remember we did that 1 through 6 homework where we had like the k equals, I don't even know what we had, 2 something, I don't even know. Remember that? That was like the c sub k blah, no? And then over here we had like the change in x sub k. That is what changes into the dx when we do the notation. And so it kind of represents like that idea of the rectangles. But you're right, when we integrate it, we don't really do anything with it, except for that should always match this. It's kind of important in separation of variables, because it lets you know which variables to put on which side and how to move them. But once you start integrating, you're right, you don't really do anything with it. It's just the notation that we use. This one's kind of cool, because when you take the integral of 1 over u, you get ln of u, and u was ln of x. So you get ln of the ln of x, which is not ln squared. That would be ln of x times ln of x. Like that would be your answer. Oh, number 10. Like I used the most paper on number 10. And then number 10 is one of those where you look in the back of the book and they do some crazy ln stuff, and you think, what? Who thinks of this?
See, a lot of like the first like 4 or 5, like if you did it where you didn't like plug the x like equation back in for 2, I got the answer in the back of the book. But if you actually plug in like the x equation, then you're supposed to do I think
It depends. When there's bounds, remember you don't have, if you change your bounds in terms of u, which I'm guessing that's what you did because you got the right answer. If you change your bounds in terms of u, you don't go back to what u was. Like you leave it in terms of u. If you plug back in what x was, you wouldn't change your bounds. So if you change your bounds, you're right, you don't go back to x, or you won't get the right answer.
like, okay, if I just did like, because I thought I did it wrong.
Yes. What's you guys are mean. So what if this was on the test? I would say, okay, can I integrate this? Well, I can't separate addition subtraction, so using algebra here probably not a good choice. I could maybe think about if I pick the denominator as my u would equal x squared minus 3x, du would equal 2x minus 3. Is there any way I can make 2x plus 6 turn into 2x minus 3? No. And so this is the strategies that I want you to be doing. These are the strategies I want you to be doing. Thinking through this, because on the test, if you say, hey, should I use a u here? Should I do this here? I'm not going to tell you because I want you thinking through it. I'm testing your knowledge, not my knowledge. So I'm with you on this. Like I would try all the other things first, and I would say, okay, that doesn't seem to work. So what's my only other option? Well, I could factor the bottom into x times x minus 3. So maybe I should try the breaking up the fractions, because I could rewrite this as a over x plus b over x minus 3. But if you take a 2 out of the top, that still doesn't match, right? Like you need a 2x minus 3. So if you take a 2 out of the top, you're right, it's close. But you take the 2 out here, the x plus 3, it has to match, or you have to be able to put a number in there to match. So you're right, it's close, but it doesn't. Close isn't good enough in calculus, unless you're doing it in a Riemann sum. That is an estimate. Get it?
So if you brought the 2 out front and left the top as x plus 3, you still set x plus 3 over x squared minus 3x equals the a over x plus b.
And then just hold that 2 out there the whole time?
Yeah.
We don't ever really, no.
It wouldn't work.
Well, because to solve for this, I don't know, maybe. Like, you have to just keep that 2 out there the whole time, so you're going to set up whole different fractions and then multiply by 2 at the end? I don't have any idea. Let's see if it works. So I tend, like, I write this out so that way I remember what goes where, but I don't really show my work very well on this anymore because I know stuff's going to cancel, right? I'm going to multiply by this, so this side I just get 2x plus 6. This side I'm just going to get a times x minus 3 plus b times x. And remember, if you switch those, that's okay. It just means your answer will be backwards from mine, but in the end it should work out the same. Then I plug in the zeros here. So if I plug in, and this is really how I write it on my paper, if x equals 3, then I say 3 times 2 is 6 plus 6 is 12. If I plug in 3 here, that goes to 0, so that would give me b times 3, so b would equal 4. Stop me if you need more work than that. Oh, Cora. And then I would plug in x equals 0 and do the same thing, so that would give me 6 equals negative 3a, so a equals negative 2. And really it's just the algebra every time. It's the same steps, factor, rewrite the fractions, plug in the zeros, so that's why I don't show very many steps in this, because it's a long enough problem as it is. Here's what's really important. Make sure you put b with your original b, right? So if b is 4, 4 has to go above my x minus 3, negative 2 has to go above my x. If you switch it, then things are going to not be the same anymore. So now I have the integral from 1 to 2 of negative 2 over x plus 4 over x minus 3. We do partial fraction decomposition because we couldn't integrate this. We can integrate this. And remember the properties of integrals. You can separate addition and subtraction. So you can do each one of those components separately. So you can take the integral of this separate from the integral of this. Also remember that the coefficients don't really matter. So if it helps you to rewrite pulling them out front, you can rewrite pulling them out front. I tend to just say, oh, I have a negative 2 here. And then I would be left with 1 over x, so that would just be ln of x, plus, I have the 4, it doesn't mean anything, because then I would just be left with 1 over x minus 3, which would also be ln of x minus 3. And since you're evaluating this, you could combine it together first, or you could just plug the numbers in. I don't know which one is better, but then you're going to evaluate that from 1 to 2. This is why it's important for absolute value bars, because if you plug a 2 in there right now, you might think you can't do it, but that's why you do absolute value, because you would just take the absolute value of it. So I just plugged my numbers in first, and then I went back and simplified. So I said negative 2 ln of 2 plus 4 ln of 1, right, because 2 minus 3. Minus negative 2 ln of 1 plus 4 ln of 2. Super great. What's the ln of 1? 0. You need to know that without a calculator, that the ln of 1 is 0. I did. I just did like 2 minus 3 is where I got this 1 from. Right? Like, so I plugged in, this is the 2 and the 2, this is the 1 and the 1. I just did the math up there already. And then remember, it's absolute value, so that's why those are positive numbers. So this goes to 0, this goes to 0, so I'm left with negative 2 ln of 2 minus 4 ln of 2. Oh, look at this, it matches perfectly with the back of the book now. Because the back of the book says it's negative 6 ln of 2. Does that make sense? Negative 2 ln of 2 minus 4 ln of 2? No, it doesn't. Here, look
Yeah,
at.
it does.
You could have written ln of 2 to the negative 2 minus ln of 2 to the 4th, right? So maybe you wrote ln of 1/4 minus ln of 16. But then you look at the back of the book and you get this. And it's just because they're doing the properties of ln's. You gotta know that when you multiply ln's, when you add ln's, you can put them together as multiplication. When you subtract ln's, that's division. And that you can put these in as exponents, right? Those are properties of logarithms. Using the exponent rules is where that comes from. So from this step, you could have said that's ln of 2 to the negative 2 divided by 2 to the 4th. When you do this, you subtract exponents, so that's 2 to the negative 6, which is where you can get negative 6 ln of 2. Do you have to get negative 6 ln of 2? No. It shows up all over this book, so I hope that you're getting better at it. When I did this on my paper, I had this as my answer. Like, I simplified it like this, and then I looked in the back of the book, and I was like, what? And then I did the work. Like, how could I get that, right? So it's not that you have to get there right away, but if you see that in the back of the book, I want your mind thinking, oh, I bet that's the property of ln's. They love to do that with ln of 2, right? Because there's so many powers of 2, I think that's why it shows up the most. But it seems like any time that there's a power of 2 with ln, they do some fancy simplifying or crazy simplifying, however you want to think about it.
On the AP test, we always get to one of those answers then, or I don't really understand where to stop.
Well, it's a multiple choice question. You stop when you can match up the answer. On a free response question, first of all, they would never give you something. It was on a free response question. But technically, on a free response question, you could stop as soon as you have all numbers, right? So, like, you could really stop right there. On a multiple choice question, are they going to have it like that? Probably not. But they do some fancy simplifying sometimes with some of the multiple choice questions. So I just like to try to show you where this stuff is coming from, because you just want to be able to match up your answers with their answers. But yeah, like any of these answers on an open-ended question would get you credit. Other questions? Slope fields, I talked to you about slope fields yesterday, and everyone I talked to said they felt terrible about slope fields, so we...
Slope fields are not hard that bad, right? They were, but right, and then
All right. Okay, we're on court. I really think that you're going to be correct.
and it was really, really awesome.
Yeah.
So if I make you graph a slope field like 37 and 38, that would be on a free response question. And they have been known to make you graph slope fields over some points. And remember, you're just doing the derivatives here. So did you say 37? Either way, both of those only have an x or y in them, and so that means that it's not as hard as when there's both an x and a y, right? When there's x and a y in the derivative, you have to look at each individual point. But like on this one, remember that if you just look at your points, and then you can think about your derivative, when x is 0 and y can be anything, your derivative is always going to be 0. So where x is 0, that would be the y-axis, your slope should be 0. So how do we draw a 0 slope? We just draw flat line. When x is 1 and y is anything, your slope is going to be negative 1. So remember, you just draw that little segment in. I always think about if I connected from this point to this point, right, that would give me a slope of negative 1. So that's how I try to look at that and think about, that's totally too steep. No, that's not. Close enough, right?
This I thought would be some magic.
Oh, yes. And so then this one would be positive 1, which would be like this. on an AP question, on a test I'm going to give you AP style, if I made you graph a slope field, whether it was easy like this or it was ugly with an X and a Y in it, it's always 2 points. 1 point for your zero and non-zero slopes, 1 point for everything else, which means for all of these, they're pretty lenient. As long as you have it going in the right direction, you show that the steeper slopes look a little steeper, they're not going to be super judgy about that, all right? But your zero slopes better be zero, undefined slopes better be either not there at all or vertical lines. The matching part is where you have to think about what you're doing. This is the derivative, right? The slope field shows you the slopes of all these points. And so then if you were going to draw in the function at the point 0, 1, right, would mean if I graph this point 0, 1, I would want to follow that slope field and think about the curve that matches that. It's just like solving the differential equation. I could say, solve this differential equation given the point 0, 1. You could integrate it, and you could find what C is using this point and get me the actual function. Slope fields do that without actually making you integrate it, because sometimes they're really ugly. This one's really nice because you can see this has a slope of 0, which means it's like turning point. And if you follow, these are all going to be positive slopes, and then on this side is going to be negative slopes. And so you can see that this would be sort of, it should be out like this. And then this is going to be out sort of, it's going to be a parabola turning down, right? And
You don't expect it to be equal, because that's what I first saw that put in, and it was working out, like, I got half of it.
right, which it doesn't say, right, construct a slope field. You couldn't do anything else with that, but you could integrate it, and you're right. When we integrate it, we would get x squared over 2, right? They're not asking you to integrate. They're not asking you to find the function. They're just asking you to draw the slope field and sketch a curve in. You're right. That would have, like, the reason it's so wide is because it would be x squared over 2, and it is going to be stretched horizontally like that. That's why it is so wide, because if you did integrate it, it would be negative x squared over 2 plus c. They gave you that. But there's no need to do that. On slope field questions on the AP test, they're going to be really ugly that you're not going to be able to integrate it very easily to help you draw the curve in. They want you using the slopes to draw the curve in to do that. I gave you that. We had a worksheet packet with the slope field with the matching. AP test does not have matching questions on it, so that's not going to be a question. But like number 11, where they get you the slope field and they ask you to find the equation that goes with it, that's an AP type question where you have to look at this and say, well, where are my zero slopes? Where are my slopes positive? Where are my slopes negative? Which one of those match that slope field up there? Or I think I gave you one on the review that asked you to draw the curve in. Did I give you number 15 to do? Yeah. Draw the curve in with the point 0, 0. And so they want you to graph that point and then sketch the curve in. Or maybe instead of sketching the curve in on a multiple choice question, they could say, here's a slope field. Which function could be the solution up there? Like, which one could it be graphed? And on number 50, did you see that it kind of looks like sine when you draw that line in? Because it starts at 0 and it goes up and then some version of sine. And so that's the idea with slope fields. Maybe, I don't know. What else you got? What about the in stuff? Do you feel okay about the solving for half-life and all that stuff? Right. Like number 55, they didn't give you the half-life of carbon-14. I would either give you the half-life of carbon-14 or give you the K value, which is doing the Harvard formula, I guess. Because on 55, depending on what you use, because one part in the book they use, what is it? 5,030, and then sometimes they use 5,700. So depending on which one you use on 55, your answer is different in the back, so I forget which one they use. Right, but then they use 730 at the beginning, so I don't know. I will give you the half-life, so we won't just assume that we all have the same value for carbon. So. multiple choice and free response. If there's a 2-hour delay, we will just do multiple choice. Okay. I will tell you on this test, like on the AP style test, there are no questions over that carrying capacity stuff, the super easy stuff, right? But on the retest, I did put questions like that, so you know, I'll test it eventually. But like it just doesn't fit really with AP style to give you a question like that. The only thing, the really good kind of question I should give you, which I wouldn't, would be like solving one of those equations, like doing separation of variables to get back to the logistic function, which I don't give you though. But like number 61 in on the review, I didn't give you that one. But if you do separation of variables on that, you end up with that logistic function, which is really ugly and awesome. That would be a good AP question, but I'm not going to. So just want to let you know you didn't have to memorize that stuff. But what is this? This is why we set a test for. We don't even know what to talk about.